I'm now going to show you the latest release of the FCMpass software. As well as performing light scatter calibration, this software allows you to perform fluorescence calibration and create automated MIFlowCyt-EV reports of your experiment with respect to the calibration and characterization fields. One of the distinct differences to the Xometry software is that this is free for academic use and is compatible with reference materials from any source. FCMpass catalogs your reference materials so that their information will automatically be completed in your MIFlowCyt-EV report, saving you time. You're also able to keep records of your calibrations and experiments over time. So today I want to take you through calibrating a dataset from start to finish with the FCMpass software. This is the new version 3 software. So these are some BD Quantibrite MESF beads, and I'm just going to show you how they were gated. So we're gated on forward scatter and side scatter here. And we'll just look at the PE channel and turn this into a histogram. And you can see each of the gates for the beads. And just to do the same with the NIST traceable beads, this is the violet side scatter height. So we've used the height here because we're defining the trigger, whereas the fluorescence channel, we are using the area statistic. And for all of these populations, we're using the median. So we're going to add a data set now, a database. So this is the University of Ottawa's Cytoflex S, where this was generated. So we'll create a cytometer where we'll store this data set. We'll click on the cytometer, and now we'll add a data set. So these data sets are, this database is made so that you can track your data sets through time for each of your instruments, which will help you keep track of your experiments, but also your instrument sensitivity. So we've now created a data set. We just need to import our FCS files now. So we'll click the plus icon, navigate to where our files are and click open. So this will now import all of our FCS files, and it will also extract some of the parameters like the threshold for each of the channels, as well as what the parameter names are. So we're going to just define these sample types first that will help with our annotation. So we're going to turn all of these NIST traceable beads into side scatter calibrators, and our fluorescent beads, our 8 peaks and our PE Quantibrites will turn into fluorescent calibrators, and the rest will just leave as standard samples. So now that that's done, we'll move on to adding a fluorescence calibration. So we can add as many of these as we like. So from our catalog, we'll pick that we want to perform a calibration using these PE MESF beads. The Quantibrites, you can see that their reference values have appeared on the right. We now select the channel that was relevant for those PE beads. And now we'll go to our data and put in the median statistics for each of the populations for the PE channel. And you can see that the parameter name there we've left as the default, which is PE MESF, but you could also edit that. In the advanced settings, you can also change the FP ratios. So now that's all done, we'll go to the scatter calibration. We decide which channel we're calibrating, which is the violet side scatter height. You can see that the scatter threshold's automatically been detected. We'll change the wavelength, and you'll see that the sheath refractive index is updated. And now we pick the bead set that we use for calibration. So this is in our catalog. It's predefined with all of the metadata. And again, we go back to our FlowJo data, and we put in all of the median channel numbers for each of these bead populations. So by default in the software, if you were going to press calibrate now, it would automatically generate models for EVs with a low, average and high refractive index, which you'll see in the table here on the right. What we need to do is add one more refractive index in to represent the virus. So this was put as 1.4546, and in the FCS file, we want this to appear as MLV diameter. So we'll just edit that in there, and that will be added to the FCS file as well now. So that's all we need to do now for the calibration, and all we have to do is press calibrate. I've left this purposely in real time so you can get an impression of how quickly this can be done. And we've essentially gone from start to finish with this calibration now in less than 10 minutes. So when all of these files are calibrated, they'll be exported to the same folder the files were imported from. There'll be a folder in there called FCMpass export and the time that the files were exported, as you can see here on the right. And in there, we've got our calibrated files. We also have our MIFlowCyt-EV spreadsheet. So this has been semi-completed now for the calibration parameters. The upper fields are for the metadata. All of the information that we could pull out of the FCS files and the catalog have been completed. So this sample acquisition info has all of your limits of detection across all of the different models you've generated. So polystyrene, silica, EVs, murine leukemia virus, and scattering cross-section. We know what the threshold was on every channel. The fluorescence calibration, we have all of the metadata, including the acquisition statistics, the reference values, slopes, intercepts, FP ratios, as well as the manufacturer information. And then finally, we have our scatter calibration. So this table just needs reformatting slightly if we make this first column smaller. But this table essentially, again, has all of the metadata associated with the model that was just generated. So we have all of the bead information in there, the refractive indices of the beads, the catalog numbers, the acquisition statistics, and everything else that you'd need to know to reproduce this model if you didn't have the FCS files. So the last output we'll look at is the quality control plots. The first page has the light scatter calibration model fits and your scatter diameter curve there down at the bottom. And the second page contains your fluorescence calibration plots. So this will just be a page full of the fluorescence regressions. So now just looking at the calibrated files, you can see when we go to the drop down with all the parameters, all of the standard parameters are at the bottom, and on the left you can see that the parameter that they were originally converted from. Something that I wanted to show you is that many of the scales might need changing. So the diameters, for example, we want to go to a linear scale, and ideally we want to look at the smaller range. Everything we're kind of interested in with this murine leukemia virus is down in the kind of 150 region. So if we put the scale to 100 to 500 nanometers, it should be sufficient. And you can see here, if I just gate around the 152 nanometer beads and the 203 nanometer beads and get the median statistic for polystyrene, we come out at 148 and 197. So we're 4 or 5 nanometers out, but we're very close. And this is how the data was generated in the paper that was published. So you can see PEMESF versus murine leukemia virus diameter here. So I've now taken you from start to finish of performing fluorescence and light scatter calibration with the FCMpass software. I really hope this has convinced you how quick and easy it can be to perform calibration, as well as the huge benefits that there are to utilizing it. I've also put some references here to the papers that are relevant to the development and the implementation of the software, as well as our website link where you can download the software. So with that, I'd like to thank our collaborators and hand over to John Nolan.